Hello everyone. Thank you for tuning into our presentation on estimating winter road surface condition, a deep learning-based approach. This research is done by Mingjin and Chan and supervised by Dr. Tae Jae Kwon. Winter roads without proper maintenance leads to safety problems and mobility issues. 17% of all car accidents occur in snowy conditions, and within them, 1,800 people die per year. Mobility is also severely affected. Depending on the level of precipitation, we can observe anywhere from 5 to 25% reduction in road capacity. It's thus important for jurisdictions to understand road conditions. To better understand road conditions, jurisdictions will use Road Weather Information System, or RWIS, to gather information like weather and pavement conditions. These information are interpreted by maintenance personnel to make more informed and timely decisions to combat winter weather, leading to improved safety and mobility. One disadvantage of using RWIS is that it provides spatially discontinuous information, providing us with only conditions of the surrounding area. Condition of the segment in between is unknown. To fill in the missing information, we can use dash camera imagery of vehicles traveling within these segments. The issue with using dash camera imagery is the sheer number of images that we must manually go through. It's simply not feasible to manually go through thousands of images to make a single road surface classification. This is the problem we're trying to tackle in this study. To develop and implement a deep learning model for automating the process of road surface conditions classification using imagery. The type of deep learning we are applying here is called a convolutional neural network, or CNN. Images are first converted into image arrays. A filter matrix in the yellow slides across the image array to output a feature matrix, shown in the pink. This feature matrix is sent into the pooling layer where the matrix size is reduced by taking the max value within a defined quadrant. The pool matrix will have additional filters applied to produce more filter matrices followed by another pooling layer to reduce the matrix size further. These two components repeat until the matrix is sufficiently small where it will be flattened into a one-dimensional array and sent into the classification layer. Here, the one-dimensional array is multiplied by a set of weights to determine the classification of our image. In our model, there are 4 classification types: bare lane, partially snow-covered, fully snow-covered, and undefined. The undefined class contains images where the road is not visible and unrelated images to test if the model can discern between roads and other random objects. To build our classification model, we manually classified over 10,000 images based on the 4 categories mentioned earlier to create our training dataset. These training dataset is then inputted into our deep learning network to construct our classification model. 2 different accuracies are taken to evaluate the performance of our model. In the blue is our training accuracy, which is evaluated based on the training dataset. Because the model has already seen the images we are testing it with, there's a chance that it has memorized the image classifications, providing us with inflated results of nearly 100%. On the right-hand side is our other accuracy measurement, validation accuracy. Here the model is tested with images it has never seen before, not used in the training process, providing us with more realistic results of 95%. We can further evaluate our model performance with the confusion matrix to see which classification it struggles with. On the right-hand side, we can see that our model classifies all 4 classes with over 90% accuracy, meaning our model is very capable of differentiating between the 4 different classes. With the trained road classification model, we can integrate it with Geostatistics to provide a spatially continuous view of the road network surface condition. By having a few observations from the RWIS point measurements, we can estimate the overall pattern of the road surface condition for unmonitored areas between the RWIS stations. Cross-validation proves its feasibility and reliability. As you can see from this graph, this combined framework informs the user the conditions of every single point of the road. For jurisdictions, they know where snow maintenance is needed, and for motorists, it informs them where they need to drive more carefully. We also wanted to look at how robust our model is, as so far our model has only been tested in the rural environment where there are few cars and trees. But how would our model fare in an urban environment where there are buildings, pedestrians, and other cars? For this purpose, we recorded images within the city of Edmonton. These images are taken from one continuous route with varying levels of snow coverage. The creation of this Edmonton model, as of now, is currently a work in progress. Before I end my presentation, I would like to thank the Alberta Ministry of Economic Development, Trade and Tourism for funding this project, as well as the Natural Sciences and Engineering Research Council of Canada for its partial funding. That concludes our presentation. Thank you for listening. If you have any questions, let us know.